We talk a lot about the scale of modern AI, the
Yeah.
billions, hundreds of billions of parameters in models like Grok 1 or GPT-3.
Right.
But the real scale, the one that actually impacts the world outside the data center, well, that's the physical infrastructure.
Absolutely.
We're talking about single training jobs that might need, over 100,000 GPUs, all running at the same time.
Easily. And when you concentrate that much computational power, you start pulling serious power from the grid.
Uh-huh.
And this introduces physical challenges that honestly go way beyond just cooling things down or paying the electric bill.
Okay.
The sheer demand, and really the speed of that demand, has introduced this critical stability constraint. We're seeing power swings large enough to pose a significant risk to the utility grid itself.
And that's the core of today's deep dive, isn't it? We're digging into a joint paper from, the absolute leaders here, Microsoft, OpenAI, NVIDIA,
Yeah, the big players.
detailing exactly how they're trying to stabilize the power consumption of these hyperscale training clusters because it fluctuates so much. So our mission today is to really get into the physics. How does AI training, which feels like a software task, how does that translate into potentially damaging, say, a power plant turbine miles away?
It really does sound like science fiction.
Yeah.
But the mechanism is surprisingly direct. The whole problem stems from the fundamental way these large models are trained. It relies on something called the bulk synchronous paradigm.
Okay, bulk synchronous paradigm. Let's unpack that synchronization part. What does bulk synchronous actually mean for power draw? How does that work dynamically?
Right. So just imagine those 100,000 GPUs or however many all working in perfect unison, like a giant orchestra.
Okay.
They basically alternate almost instantly between two main phases. First, you've got the compute phase. That's when they're doing the heavy lifting, calculating, running matrix multiplications. Exactly. And pulling maximum power right up near their thermal design power, their TDP limit. Got it. Full throttle.
Then, just as suddenly, every single GPU transitions into the second phase, communication. They stop computing to sync up data, exchange gradients across the whole cluster.
And during that synchronization phase, they're basically waiting, sitting idle.
Pretty much. Yeah, they drop way down, close to idle power levels.
Ah.
So picture this. The entire cluster, a facility that could be pulling hundreds of megawatts, is essentially flipping a collective switch from full power to almost off and back again, and this happens multiple times every second.
Wow. Okay, so that synchronized power swing, that rapid on-off across the whole system, that's the threat. That's where the software speed hits the physical grid mechanic.
That's precisely it. When you have this lockstep behavior across, tens or hundreds of thousands of nodes, the size, the amplitude of these swings gets enormous. You can see them at the rack level, at the data center level, and even further upstream at the grid level. We're talking oscillations potentially in the range of tens, maybe even hundreds of megawatts. Hundreds of megawatts swinging up and down multiple times a second. But as the source material really hammers home, the really shocking part isn't just how much power is changing.
Right.
It's the frequency, the speed at which those changes happen.
That's the absolute critical piece. These cyclical load changes, they tend to happen in a specific band, roughly between 0.2 and 3 hertz, 0.2 to 3 cycles per second.
Which sounds incredibly slow if you're thinking about computer clocks.
Right, glacial in computing terms.
But you're saying that's devastatingly fast for grid infrastructure.
Exactly. It's a terrible frequency for the grid.
Why? Why is that specific sort of low frequency range such a problem for, massive machines like power turbines?
Well, it's because that particular range aligns almost perfectly with the natural mechanical frequencies of the generation equipment itself.
Oh, okay. Like hitting the resonant frequency of a wine glass?
Sort of, yeah, but on a much, much bigger and more dangerous scale. Specifically, these oscillations can excite what engineers call torsional resonances in the upstream turbine generator powertrains.
Torsional resonance. That sounds bad. It means the actual physical shaft connecting the turbine to the generator starts vibrating.
Twisting.
Precisely. It starts twisting back and forth against itself. And if that oscillation goes on for too long in that critical frequency range, you risk mechanical fatigue, microfractures developing in the metal, and potentially, catastrophic shaft failure, breaking the shaft.
Wow.
And this is apparently especially true for the big high-speed two-pole turbine designs you often find in thermal or nuclear plants. They're particularly sensitive to harmonics in that lower frequency range.
That's just incredible to think that the timing, the latency of a software update syncing across GPUs need to be managed carefully to avoid physically stressing a massive steel shaft miles away at the power plant.
It's the sort of hidden physics constraint that emerges when you operate at this enormous scale. And it doesn't stop there.
These rapid cyclical power swings can also excite resonant modes in the transmission network itself, the wires and transformers. This can lead to something called subsynchronous resonance, or SSR.
SSR, okay, what does that do?
SSR is really dangerous because it can cause the power flow to lock into an unstable oscillation, which can build up. Utility providers actually have systems designed specifically to try and damp this out. Plus, you can get visible voltage flicker for consumers. It's a genuine critical infrastructure risk.
Okay, so the utilities, they obviously see this massive new type of load coming online, huge, and oscillating rapidly. They must have stepped in with some hard rules, some specifications.
Oh, absolutely. They've had to.
What kind of requirements are these data centers facing now?
They generally fall into two main categories, time domain specs and frequency domain specs.
Okay.
Time domain specs deal with the raw speed of change. Utilities will mandate a maximum allowed ramp-up rate and ramp-down rate, basically how many megawatts per second the load is allowed to increase or decrease.
Right, the slope of the power change.
Exactly. And they also specify an allowed short-term deviation, sometimes called the dynamic power range, over very short intervals, like sub-second intervals, how much it can bounce around quickly.
Okay, that makes sense. And the frequency domain specs, those must be the ones targeting that resonance problem, trying to avoid shaking the turbines apart.
Correct. The specs focus on that critical frequency range we talked about, often somewhere between, say, 0.1 and 20 hertz. And they basically put a cap on the amount of energy fluctuation that's allowed to fall within that dangerous band. They might say, for example, that no more than 20% of the total harmonic energy can be in that range.
And the problem is, these AI workloads are naturally operating right in the middle of those danger zones.
Pretty much. Whether you're talking about the very low frequency resonance of long transmission lines, which can be below 1 hertz, or the higher frequencies linked to the natural modes of the turbine shafts themselves, which can range from 7 hertz up to over 100 hertz, the AI power swings are just in a bad spot.
Okay, so the problem's clear. The load is huge, it's synchronized across the whole cluster, and crucially, it's oscillating at frequencies that threaten the physical grid. Let's pivot to solutions. How are these engineers, from Microsoft, NVIDIA, OpenAI, how are they tackling this? It seems like a physics problem almost.
It really bridges the gap between software and physics.
Let's start with the first approach they mention, the software-only solution. They gave it a cool name, the Firefly approach.
Yeah, Firefly. It's actually quite clever in its basic concept. The idea is to eliminate that power gap, the drop during the communication phase, by using computation itself.
How?
During that low-power communication phase, the system dynamically injects a secondary power-hungry workload onto the GPUs.
Okay.
This could be just running matrix multiplications, GMM kernels, basically burning cycles, or perhaps it could be running a lower priority but still useful background job. But its main function in this context is just to draw power.
To keep the lights on, metaphorically speaking, on the GPU.
Exactly. To artificially maintain a minimum power floor, smoothing out the drop.
So it's like using the GPU as a dynamic brake or maybe a heater just to keep the power draw from collapsing too quickly.
That's a good way to think about it. The big advantage here is flexibility, right? And it's relatively quick to deploy. You don't need new hardware, no new physical infrastructure.
But there have to be downsides. What are the trade-offs?
Oh, they're significant. Firstly, if that secondary workload is purely artificial, if you're just running math problems to generate heat, you are fundamentally wasting energy. Lots of it.
Yeah, that seems like a major issue, especially given the scale. And the source mentioned the monitoring cost. It sounded intense.
It is. To make this work effectively, especially fast enough to counteract those millisecond-level fluctuations, you need incredibly fine-grained, real-time monitoring.
Like how fast?
We're talking 1 millisecond granularity telemetry of each GPU's power draw. Continuously. And collecting and processing that data requires dedicating host CPU cores and significant internal network bandwidth just for the monitoring and control loop to deploy that filler workload instantly.
Okay.
Plus, while they apparently managed to limit the performance hit on the main AI training job to under 5%, which is pretty good, they have to use shared GPU resources.
What does that mean in practice?
It means if the power smoothing background job crashes or has an error, it can potentially take down the primary mission-critical AI training job along with it. So it reduces overall reliability, especially at massive scale.
Okay, so that lack of reliability, the wasted energy, the high resource overhead, That kind of pushes towards the second solution they discussed,
Right.
building the smoothing capability right into the silicon itself, the GPU power smoothing approach.
Right. This is more of a hardware firmware solution. It's something we're seeing in newer architectures, like NVIDIA's GB200 platform.
How does that work?
It basically allows the data center operator, or the system, to program preset power profiles directly into the GPU's own power controller, very low level.
What kind of settings?
Things like setting a minimum power floor, MPF, the lowest power level the GPU is allowed to drop to. You can also program the maximum ramp-up rate, maximum ramp-down rate, and even a stop delay.
Okay, so because this uses the GPU's own hardware features, it should be really fast, right? And presumably more reliable than the software juggling act.
Exactly. Much faster response time, much higher reliability. It doesn't depend on complex external software trying to coordinate everything across the cluster.
Yeah, I feel a butt coming.
We
We run right back into that sustainability question, don't we? Wasted energy.
We certainly do. While it's reliable, the primary drawback is still the energy wasted just to maintain that artificially high power floor.
How much waste are we talking?
Well, the paper includes a simulation using a real training workload's power waveform. It showed that setting the minimum power floor to 90% of the GPU's maximum power, TDP, resulted in a 10.5% increase in total energy consumption for the job.
Wow, over 10% extra energy burned just to flatten the curve.
Yeah, you're paying a significant energy penalty just to meet the grid stability requirements.
Okay, let me push back on that a bit. We're talking about a hyperscale AI industry where these models already consume mind-boggling amounts of power, sometimes rivaling small cities.
Sure.
Are we really comfortable just accepting a solution that mandates wasting another 10% or more that total energy, potentially forever, just to meet a utility spec? That feels, well, unsustainable, especially if we're trying to be climate conscious.
That is the fundamental dilemma the industry is grappling with right now. It's essentially a forced trade-off. Sacrifice energy efficiency to guarantee grid stability. And what's more, even with that 10.5% energy waste, the current hardware limits might still be a bottleneck. For instance, the paper notes that if a utility has a really strict requirement for the dynamic power range, say, demanding fluctuations be kept under 10% of the total power.
Right.
Well, a 90% minimum power floor still leaves a 10% gap between that floor and the peak power draw, assuming peak is 100% TDP. So the hardware feature alone, as it currently exists, might not even be enough to meet the absolute tightest utility specs in all cases.
Okay. So if software is wasteful and unreliable, and hardware smoothing is also wasteful and maybe not quite tight enough, we naturally move to the third option, the physical infrastructure solution. Rack-level energy storage. Batteries, basically.
Batteries or large capacitors, yeah. This is arguably the most elegant solution from a pure energy efficiency perspective.
How does it work?
You deploy energy storage systems, think batteries or supercapacitors, right there at the server rack level.
Okay, close to the GPUs.
Very close. The idea is simple. The storage charges up during that low-power communication phase when the GPUs are idle. And then it instantly discharges during the high-power compute phase, supplying that peak current locally.
So it acts like a local buffer, smoothing out the load that the main grid actually sees.
Precisely. It makes the power draw look much more constant from the perspective of the utility connection.
And the huge advantage you're saying is that this doesn't inherently waste energy like the other methods. It just time shifts it locally.
Exactly.
Yeah.
It's a massive potential win for operational costs and overall energy efficiency. The researchers also point out that putting the storage at the rack level makes a lot of sense.
Why there specifically?
Well, the AC to DC power conversion infrastructure is already located there in modern data centers. Plus, distributing the storage across many racks improves the overall resilience. It's better than having one single massive battery bank for the whole data center, which would be a single point of failure.
Okay, if it's the most energy efficient, what's the catch? I mean, besides the obvious upfront cost, which must be huge.
Yeah, the initial capital expenditure is definitely a major hurdle. You've got the cost of the batteries or capacitors themselves, the physical rack space they consume, and you also have to consider the embodied carbon footprint involved in manufacturing all that storage. But there's a technical challenge too, particularly around handling those extremely fast ramp-up and ramp-down phases, the moments the GPUs switch between compute and communication.
Why is that hard for batteries?
To supply the massive, almost instantaneous surge of power needed during ramp-up or absorb it during ramp-down, you need storage with very, very large power capacity, high C rate. and extremely low internal resistance.
Okay.
Designing and deploying storage that's potentially oversized just to handle these very brief, high-power transient events can make the whole system economically inefficient. You're paying a lot for capacity you only use for milliseconds at a time.
It really feels like none of these three options, software smoothing, hardware smoothing, or local storage, is a perfect silver bullet on its own.
No, they each have pretty significant drawbacks.
Which leads us logically to what the paper proposes as the comprehensive solution. A hybrid approach, mixing and matching.
That seems to be the consensus, yeah.
Yeah.
The papers strongly advocate for a multi-pronged solution that really plays to the strengths of each method.
So what does that look like?
The core idea seems to be combining the GPU power smoothing features, which are great for handling those very fast time domain ramp specifications, and acting as a sort of local, instantaneous backstop.
Right.
With the rack-level energy storage, which handles the bulk of the power swing efficiently and without wasting energy during the steady compute communicate phases.
But that sounds like it requires some serious coordination, doesn't it? The storage system and the GPUs can't just operate in isolation. They need to talk to each other.
Absolutely critical. The paper stresses the need for co-design. The overall system needs to be aware of the state of charge of the rack-level batteries or capacitors.
Why?
So that the built-in GPU smoothing only needs to kick in when absolutely necessary, maybe as a final fast response if the battery is momentarily depleted, or perhaps just to manage those millisecond-long ramp speed transitions precisely while the storage handles the sustained high-power draw efficiently without burning extra compute cycles.
Okay, so you've got hardware smoothing for the fast ramps, battery storage for the bulk swings, but even with all that, they still say you need one more layer, a fast telemetry-based backstop system. Why the extra fail-safe?
It's because, even with the best-laid plans, resonance issues could still potentially emerge, maybe due to unforeseen interactions with the wider grid or some unexpected harmonic behavior in the AI training algorithm itself under certain conditions.
Ah, okay. Murphy's Law for power grids.
Pretty much. So this backstop system acts as a final safety net. It continuously monitors the power waveforms coming out of the facility, performs real-time spectral analysis, usually using fast Fourier transforms or FFTs.
Looking for those dangerous frequencies.
Exactly. It's constantly checking FFT bins to see if any problematic frequencies related to grid resonance are starting to spike up in the system's power signature.
And if the system does detect a dangerous frequency starting to climb, getting close to one of those critical turbine or transmission line resonance points, what does the response look like? You can't just flip a switch on 100 megawatts instantly, can you?
No, you need a tiered response. The system would likely initiate steps based on severity. The first responses would be soft, things like dynamically reshaping the load slightly, or maybe gently throttling the AI workload to reduce the amplitude of the oscillation.
Trying to nudge it away from the danger zone.
Right. But if the problem persists, or the detected frequency gets dangerously close to a known resonance point, and the risk of excitation is high, then the ultimate response has to be more drastic.
Like what?
Coordinated circuit-level power shedding. Essentially, starting to selectively and rapidly disconnect parts of the load in a controlled manner. This has to be tightly integrated with the data center's power infrastructure logic to prevent causing new instability problems or cascading failures further upstream.
Wow. The sheer complexity here, it really underscores that the solution isn't just about, Microsoft or NVIDIA designing a better GPU or battery. This requires collaboration across the entire ecosystem, doesn't it? Tech and energy have to work together.
That's the absolutely crucial call to action that comes through in the research. It's a multi-stakeholder problem.
Who needs to do what?
Well, first, the folks designing the AI frameworks and the large-scale systems they need to actively explore and develop training algorithms that are inherently less synchronous, more power-aware from the start.
Like staggering the communication phases, so not all 100,000 GPUs sync at the exact same microsecond.
Exactly. Things like staggered scheduling, asynchronous approaches where possible, anything to break up that perfect, problematic lockstep behavior. Second, the grid providers, the utilities, need to be open partners.
How so?
They need to be transparent and share their specific grid characteristics, the resonance frequencies, the ramp rate limitations for specific substations. Data centers can't design compliant systems if they don't know the precise specs they need to meet for that part of the grid they're connecting to.
Makes sense. You can't hit a target you can't see.
Precisely. And finally, the industry as a whole needs open standards. Standards for the telemetry data, for the mitigation controls, perhaps through collaborative forums like the Open Compute Project, OCP. This ensures that everyone building these hyperscale facilities is working with compatible, effective stabilization tools and techniques.
This has been a really fascinating deep dive. It opens up this whole hidden layer beneath the AI software.
Mhm.
The key takeaway for me is crystal clear. It's the sheer scale, yes, but critically, it's the perfect, rigid synchronicity of modern AI training that transforms what looks like a software optimization issue into a fundamental threat to utility grid stability.
Mhm.
And solving it requires tackling it simultaneously from all angles: the software logic, the specialized hardware in the chips, and the physical power infrastructure itself.
We're definitely entering an era where, for these massive foundational models, power engineering expertise is becoming just as vital as computer science expertise. They have to go hand in hand.
Absolutely. So here's a final provocative thought for you, our listener, to maybe chew on. Given that tough trade-off we discussed, the one between raw performance, like training speed and latency, versus the wasted energy required for power smoothing techniques.
Right, the efficiency versus stability problem.
Exactly. Will future foundational models need to be intentionally designed to be perhaps slightly less computationally efficient, maybe a tiny bit slower, if that's the unavoidable price we have to pay to keep the lights on, quite literally, for everyone else? Is the age of optimizing only for peak computational speed starting to hit a hard physical limit imposed by the power grid?